Hi, and welcome to Lesson 6. This Lesson 6 is all about materials, and it's important to note that I'm not an engineer. I'm not a specialist in materials, but that doesn't mean that understanding the basics about materials isn't important for me. It is, because I have to produce parts, and to be able to produce accurate parts, I have to understand at least a little bit about how materials function. So remember, this is an introduction to materials, really just a way to make some sense of how the world works around us. Now, we already have several videos that talk about materials. We have a Recognizing Steels video. We have a Tips and Tricks videos of how to identify different steels and their state, how hard they are. We have a couple of videos on heat treatment that help us understand how steel can be hardened. And we have a couple of videos on chip formation that really have a lot to do with materials, in that case mostly steel, but materials properties. More specifically in this video, we're going to be looking at atoms, elements, and molecules, or in other words, what holds everything together. We're also going to be looking at non-ferrous metals, since we've already covered ferrous metals in other videos. So we're going to be mostly talking about aluminum, brass, and bronze, and their alloys. We're also going to be looking at ceramics. Ceramics as in a cup of tea? Well, perhaps, yeah, why not? But also ceramics for us in the machine shop as far as carbide inserts and that type of super abrasive ceramics that we use. So we're going to be talking about ceramics, and we're going to be talking about plastics. Now, plastics is one of those words that can tend or lend to confusion. So we're going to be calling them polymers. And polymers are a big part of the shop these days. More and more parts are being produced in polymers. So that's something that will be important. Now, there are smaller particles, but for us, we're going to start the story at the level of the atom. And atoms are composed of different particles. We have protons, we have neutrons, and we have electrons. Those basic components are organized into two parts: a nucleus that's made up of neutrons and protons, and that has a positive charge, and that makes sense because neutrons are neutral, protons are positive, and that nucleus is surrounded by electrons. And the electrons, well, they have a negative charge. The nucleus is often looked at as being a rather passive accumulation of neutrons and protons. And the electrons are often looked at like moons orbiting that nucleus. Well, it's a little more dynamic than that. Now, the nucleus is a stable thing, but it's not boring, because the protons want to push away from each other. They're all positive, and we know that opposites attract, but sames repulse. So they want to push away from each other. And the neutrons, well, they're just mixed in between. And that's all held together by something that's called the nuclear force. Nuclear force, nucleus. I guess they weren't very inspired on the day that they were giving out names. And that nuclear force, well, is quite important, because the nucleus is the anchor of the whole deal. It's the stable part. It's the part around which revolves those electrons. The electrons, however, are real movers, and they're buzzing all around the nucleus. And that's why I don't like to describe them as being in orbit around the nucleus. They are, but they're moving so fast that it really doesn't sound like something that's in orbit. They form actually something that's more like a cloud around the nucleus. And we can get a feeling for that by using a laser, not a laser printer, a laser pointer. Now, if I use this and I aim at the whiteboard over there and I spin in a circular motion. Well, if I can spin fast enough, I end up producing something that looks like a shape, even though it's just a dot. Now imagine that same circular motion around the nucleus of the atom. Okay, so those electrons are spinning all over, but not in one plane. Well, obviously it's not because there's so many of them, but seen as they're moving so quick, they end up looking like a shell or a cloud around the nucleus. The number of protons in an atom's nucleus determines what element we're looking at. So iron doesn't have the same number of protons as lead does, or as gold or aluminum does. So that's an important number, and we call that number, the number of protons, the element's atomic number. And all elements are organized in what's called a periodic table of elements by their atomic number. And no, there's no reason to learn the table by heart for working in machine shop. No, it's just nice to know that those are the elements that make up everything that surrounds us. Our electrons are buzzing around our nucleus. And that's important, and it's important to say that there are different levels of electrons. And the electrons that are furthest away from the nucleus of an atom, well, they're called valence electrons. And they're important because they're the ones that are generally responsible for holding things together. Now, why is that important? Well, if we can't hold atoms together, well, we don't have properties. And what does that mean? Well, look. If I have a blob of gold, well, that piece of gold is shiny. And that piece of gold can conduct electricity. And that piece of gold can be ductile and malleable. Because it's a group of atoms, and they can have a property. But an atom of gold cannot conduct electricity. An atom of gold cannot be malleable or ductile. An atom of gold, I'm guessing, can be shiny. I don't know. No one's ever seen it. But for atoms to acquire properties, we have to group them together. And if we're going to group them together, well, they have to bond to one another. And that's where valence electrons come into play. So what holds atoms one to the other? Well, it's the same type of electromagnetic force that held the electrons in orbit around the nucleus. Okay, negative electrons, positive nucleus, attraction. Well, it's the same thing. It's a play on what atoms and their valence electrons create a positive or a negative, and how can they stick together. And their bonds, okay, like that, nuclear bonds between atoms, well, they are of three basic types. We have ionic bonds, covalent bonds, and metallic bonds. First thing that's important to state is that you can't just join anything with anything in any way. Certain atoms will join readily, and certain atoms will join readily using one type of bonding and not the other. So it really depends on where they're positioned on the periodic table, or if you prefer, their atomic number. That being said, we have three different types of bonds, and the two first that I mentioned, the ionic and covalent, we're talking bare bones basics here. The two first that I mentioned, ionic and covalent, well, they're the type of bonds that are very stable, where there is an exchange and a balance point between atoms that makes everything fall into to equilibrium, really. Okay, and that's the type of bonds that we have for our example, ceramic tools. Okay, ionic and covalent bonds create very strong and stable materials. Materials that are quite resistant to wear and quite resistant to heat. And since resistance to heat and electrical isolation work together quite often, well, we know that they'll be good electrical insulators as well. So that is our ionic and covalent bonds. And how do they work? Basically, atoms hold together by electromagnetic attraction. Okay, so it's almost like the same force that held the electrons around the nucleus of the atom. So, electromagnetic force. Okay, so we have valence electrons around two atom nuclei, and we force the two one close to the other. In a valence bond, well, everything is fine and dandy, and we just force them together to a certain point where things will come in balance. Some of the electrons of one are interchanging with some of the electrons of the other. Everyone still has their own electrons, but they're not quite sure. So they're going to stick with that partner, not another partner, with that partner, and keep exchanging those electrons. They're in balance. They're pushing away at each other, and they're pulling towards each other in an even way. And we get that by forcing them one into the other. By using what? All kinds of energy. Okay, it could be heat, could be pressure, could be all kinds of things. And that's covalent bonds, okay? Ionic bonds, well, similar thing. It's always a balance, electromagnetic balance. But in an ionic bond, one of the two is missing an electron. Let's put it that way, okay? So it's actively looking to add an electron to it. And it snuggles up to another atom close by. Now, obviously, this atom wants to keep all its electrons, and this one, well, would sure like to pilfer one from the other guy there. So if he doesn't let go and he really wants to share, well, they're going to get up close and they're going to put one electron in common, okay? So they're going to balance themselves out that way, and that would be an ionic bond. Metallic bonds, however, well, they're just crazy, because metals have very loose valence electrons. Like, they don't really care about them very much, and they don't pay much attention to them. All they know is that they need them to be around, but what or whose, they don't care. And we can see that in the metal's properties. Now, if I can take a piece of sheet aluminum and bend it like that, well, that's because there's something going on in this material that'll make it ductile like that, okay, or malleable. Something that's dynamic, something that means that the atoms can exchange partners and still stay in one piece. Because when I bend that, I'm changing all the alignment of all the atoms that are in that bend. But the part doesn't fall into two parts for that. It remains intact. And that's because there's a dynamic aspect to metal bonds. And why is that? Well, it's the loose valence electrons. Now, let's say I'm an atom of iron here, and I have loose valence electrons. And here comes another atom of iron, and it pilfers one of my electrons. I'm now missing an electron. I don't like that. I instantaneously turn around, and I only have two hands, so I'd have to imagine another hand over here. I'm immediately going to turn around and take an electron from another guy, and from another guy, and from another guy, and from another guy, and all this at the speed of light. I mean, this is very, very rapid, almost instantaneous. But what I end up with is a perpetual motion, a perpetual exchange of electrons in the metallic structure. And that is the metallic bond. That's how they manage to balance things out. It's actually not a balance at all. It's just an eternal exchange of those very loose valence electrons. And that's what gives metals its property. That's why I can bend a piece of metal and that it won't break, because as I'm bending it, I'm changing all the partnerships around. And the atoms don't really care, because they have no fixed partners like they had with the valent or ionic bonds. they don't really care what's going on. They don't care whose electron they have as long as they have it, and they'll exchange with anyone instantaneously. So it's very dynamic. And that's why they conduct heat that well. Metals are heat conductive, and that's why they conduct electricity that well, and that's why they're malleable, and that's why they're ductile, and that's why they're shiny. So we can see that the metal's properties has a lot to do with how the atoms in it are held together. So we have ionic and covalent bonds, and we have metallic bonds. Now, the first two had to do with our ceramic materials, hard, strong, heat-resistant materials, good insulators. And the latter, the metallic, will have to do with our metals. And they are dynamic bonds, things that move. We got malleability, we have heat transfer, we have electrical conductivity. But it's a little more complex than that, because we know that there's more than just elements. Brass is not an element. Copper and zinc are elements. But if I mix copper and zinc together, I get brass. Brass is a compound. A material made up of two or more different elements is a compound, as long as that mix is a chemical bond mix, and we'll see why in a little while. So our brass is a compound because it's made up of copper and zinc. But to be a little more accurate, we should say that when we have a compound that's made up of different metals, well, in those cases we call them alloys. But be careful, metals don't only mix with metals. We can have physical or chemical bonds, I should say, that bond metals to non-metal elements. And a good example of that is steel. Plain carbon steel is a compound made up of iron and carbon chemically bonded. Now, we know that there are such things as alloy steel, but plain carbon steel isn't an alloy because it's not a mix of two metals or more. Alloyed carbon steels like 4140, not plain carbon steels like 1040, but alloy carbon steels, well, they still have iron and carbon in them, but they also have other metallic elements added to alter their properties. So when we talk about metals, we're really talking about three different things. We have pure metals that, if reduced to their simplest expression, end up being an atom, or if you prefer, one single element on the periodic table of elements. We have compounds that are mixes of metals or a metal with something that is not a metal. And a good example of that is our plain carbon steels, low, medium, or high. Now, if I don't have carbon in my iron, well, it's not a steel anymore, it's just iron, and that's a pure element. But if I do mix iron and carbon, well, then I end up with what we call steel. And we have alloys. So that's a mix of two metals, and if I reduce that to its simplest expression, I end up with a molecule that's made up of two or more different metals. Now, compounds and alloys aren't linear things. So if I mix two metals together and they're two soft metals to form an alloy, I mustn't or shouldn't expect the result to be a soft metal. The properties of an alloy don't necessarily and don't often reflect the properties of the original two or three metals used to form the alloy. And a good example of that is bronze. If I mix copper, which is a soft metal, with aluminum, which is again a soft metal, and I alloy them together, I end up with what we call aluminum bronze. And that is a hard and brittle material, not at all a reflection of the properties of the two base or elemental metals used to produce or to form that new material. So we have our elements, we have our compounds, and we have our alloys. But there's still something missing. And what's missing here is composite materials. Now, composites aren't compounds. Composites are something else. And a good example of that would be this fiberglass bar. This fiberglass bar is made up of two main materials. A polymer resin that's quite hard and very resistant in compression, and a glass fiber mat that is very flexible but also extremely strong in traction. And they are mechanically linked, and that means that this is not a chemical bond. The glass weave maintains its properties because I never change what it is. It is still glass weave, and the hardened polymer is still the hardened polymer. Now, if they were both separate, my polymer would break easily if I tried to bend it this way, because it's only resistant in compression and very weak in traction. And again, if this were only glass fiber, well, I would have something that would have no structure, because it would be very strong in traction, like a rope, but it would be very weak as far as maintaining its shape and rigidity goes. So with composite materials, what's important to remember is that each part, each component of the material retains its original properties. Now, fiberglass, we've just seen. What else can we say? Well, how about chrome plating? When I chrome plate something, I'm really creating a composite material. Now, we never talk about chrome-plated bumpers as being composite materials, but they are. I'm maintaining the chrome's ability to repel corrosion and usually have nice appearance, and I'm protecting the steel bumper underneath it from those problems. So I have the strength and the low cost of the steel bumper, plus the appearance and the corrosion resistance of the chrome. I don't want to lose those properties. I want to exploit them. And for that reason, I have chrome plating. Gold plating, same thing. But what else? I mean, we're surrounded with composite materials. If I have a milk carton that's a mix of cardboard and wax, well, obviously the wax remains wax and the cardboard remains cardboard. They each have their properties, and mixed together they form something that will contain a liquid. And in the shop we have something that we'd never consider being a composite material, but that is emery cloth, that we use almost every day in the shop. Emery cloth is a composite. We have the strength in traction and flexibility of the cloth mixed with the hardness and abrasive cutting power of the grit that's bonded to it. It's a composite material. When we were talking about this composite bar, I mentioned that it was made of glass fiber and a polymerized resin. And that's something that we haven't spoken about yet. Now, I try and avoid using the term plastics when I'm talking about polymers, because plasticity is more of a property than a material. Some polymers are very plastic, but other polymers are quite hard and rigid. And we just have to listen to this bar hit the ground to know that that is not soft and plastic. So polymers is the term I tend to use. Polymer. It means many molecules, because that's what a polymer is. It's a long chain or a large mass of complex molecules that we call hydrocarbons. Hydrocarbons are complex molecules that are brought into being by living organisms. Photosynthesis is at the base of all polymers because it's at the base of all living things. Hydrocarbons are complex molecules that come to us through life. Things have to live to be able to form hydrocarbons. It's not something we can easily produce. So that means that they come from all kinds of venues. Natural rubber comes from the sap of a tree. But most hydrocarbons and most polymers come to us through oil, refined oil, as is the case for the casing of this laser level and a lot of the components on it. Those complex hydrocarbon molecules link together to form long chains, and how those chains link between themselves determines a lot of the properties of a polymer. In other words, if we have just long chains, something like a piece of spaghetti, well, we're going to have a polymer that is quite plastic and that oftentimes can be remolded. If we have a bidimensional setup, something with lateral connections between the chains, well, we're going to have elastomers, rubber in other words, or things that are very elastic. And if we have really something that has a three-dimensional matrix to it, okay, a real length in all directions, well, we're going to have very rigid and very hard plastics. So polymers are something that we really want to look into, but not today. This is enough for our introduction to materials part of this lesson 6. We're going to be looking at in part 2 and probably part 3 our non-ferrous metals and our polymers. So we're going to be taking a deeper look into those things. And this stops here, but you still have a lot of work to do because we have 4 videos already in existence that present to us ferrous metals and a lot of their properties. And here's a link to those videos, the same links that we had at the start of this video. And also there's 2 videos about chip formation that tells us a lot about metals properties. So that would be good to take a look at before our part 2 video of this materials course comes out. So until then, well, have fun, be safe, and happy machining.